So if we're dealing with a material that can't support a shear stress, then eventually it's going to rearrange itself to find this condition that we call hydrostatic equilibrium. So a good example would be if I take a material and I deform it and let it flow for a while, it'll eventually come to a point where if it's a Newtonian fluid, as we just described, then it'll find a new equilibrium shape where it'll form a material shape where it no longer has any shear stress acting on it. So this would be an example with a water bottle, but even if you take something like a hand sanitizer or a material like that, it will still also flow, and you can see that it takes some time now for the viscous stresses in the material to rearrange, but eventually it comes to the same equilibrium shape that we deal with in this material. So although viscosity will set the time scale at which this happens, eventually when the system comes to equilibrium, there are no shear stresses acting on the material, and so we'll think about the system as having achieved its hydrostatic equilibrium. And so we might think about a container, and our material will form or find a shape where eventually there are no shear stresses, and so the only balance of forces is given by gravity. The body force is balanced by the normal stresses or the normal force per area, which is a stress, acting at the boundary. And so hydrostatics that we're going to be interested in the next couple of classes is going to be thinking about what is the distribution of forces that do this, but we'll essentially have a gravitational body force acting on this, and then somewhere distributed over this we'll find that there's locally a normal force acting everywhere on the bottom of the container that is supporting the weight of the fluid. Now that's easy if we're dealing with a material like this where maybe we have a rigid boundary. It becomes less easy to think about if we're dealing with, let's say, thinking about a balloon. So let's say that we take a water balloon and we fill it with water. When it comes to equilibrium and there's no longer any flow, it may be sitting on a surface that would look like this. But the material inside will still rearrange itself so that it flows to find an equilibrium shape. And again, there will be a normal force per unit area acting on the material at every single point in on the boundary. And the pressures will be larger at the bottom and progressively smaller at the top. So we're going to have to deal with thinking about how shapes come to equilibrium like that. This leads to a corollary when we said that materials were either solid, like the container that this is in, or liquid or fluid that flows inside here, is that there's actually two different kinds of fluids. So if we think about fluids, there are two different classes that we have to think about. One of them are liquids. And the second one are essentially gases or vapor, which are clearly very different in the way that they respond and the kind of equilibrium shapes that they take. So liquids essentially the volume changes very little upon deformation. And so as it arranges itself, it assumes the shape of the container it's in. But its volume doesn't change. And instead, it'll come to equilibrium with a free surface. So just as I've drawn in either of these examples over here, there's a headspace or a space above the material where there is no liquid. But this interface here is going to be characterized by a property that is called the surface tension, which limits the deformation or constrains the shape of the material. And we're going to call that surface tension sigma. And as we'll see later in the course, that has units of newtons per meter. And so that's going to be an important force. That's a force that depends on the surface area that's available. But essentially, the volume of liquid in here is the same, always the same. So when I bring this to equilibrium, no matter what orientation is, you can see that eventually the material comes to equilibrium with a free surface. By contrast, if we deal with gases or vapor or plasma, then it is strongly coupled. The response of the system is strongly coupled to the temperature and pressure of the system. So this is a strongly coupled system. To the state or the thermodynamic state, which is set by the pressure and temperature. And our fluid expands to fill the entire container with no free surface. So frequently you'll hear people talk about the thermodynamics of a strongly coupled system, like a gas or a vapor. And alternatively, if we're dealing with a liquid, then it changes very little. And so people will often call this a weakly coupled thermodynamic system. And this will be much easier for us to deal with because we don't have to worry about changes in the density as a function of the external conditions on the system. So here's a very fluid-centric view of the world as put together by Keith Moffat, professor of fluid mechanics at the Department of Applied Math and Theoretical Physics in Cambridge in the UK, which kind of shows the idea that fluid mechanics is something that you might be interested in many, many different branches of engineering. So by background, I'm a chemical engineer, and I'm very interested in non-Newtonian fluids, as we just talked about, and that's frequently discussed under the field of rheology. And there's many, many other kinds of materials, including blood and multi-phase materials, where chemical engineers and biological engineers are interested in fluids. For mechanical engineers and aerospace engineers, of course, people are very interested in design of wings and lifting surfaces, minimizing drag, minimizing noise. And here we frequently have to think about transitions to supersonic flows. If you're interested in geophysics or in geology, then you're frequently interested in transport in the ocean or pollution and smoke. Again, it still comes down to fluid mechanics. Even if you're more interested in mathematics and differential equations, turbulence and thinking about how to analyze the equations that we're going to develop, which are very complicated nonlinear partial differential equations, there's a lot of interest and challenge still for people who are interested in mathematics. And then for civil engineers, people are interested in bridge design or erosion or wave transport. Civil and nautical engineers will find many, many interests in fluid mechanics. So this is just a way of saying that it doesn't matter what branch of engineering or science that you're interested in, there's some challenges for you in the field of fluid mechanics.